problem that involves a roller coaster going down a hill, and we're going to approximate the hill using the cosine function, and we are incorporating friction in this case, and we're asked at x equal to 75 feet if and the coaster is moving at 40 feet per second with a coefficient of 0.2. Let's see if we can determine what the normal force is that's exerted by the track and find the acceleration of the roller coaster down the hill, given that the weight of the coaster is 2,000 pounds. Now, this type of problem where we have a path denoted by some geometric function lends itself very nicely to a tangent normal coordinate frame. Now recall in our tangent normal coordinate frames that if we have a path of motion, we would have a velocity along that path, v, and that velocity defines the tangent direction, t hat as we call it, which is our unit tangent vector, and then perpendicular to it is the n hat, the unit normal direction, and that points off to some radius of curvature center, where we'll use rho as our radius of curvature, and O is a temporary center of this point along the path. And that radius of curvature would have a sweep rate, which we would define as beta dot. And the way we look at it, V would be rho beta dot, which is just your r omega type of rotational velocity. And this defines the normal tangent frame. So V defines the path along the t hat, and n is always perpendicular to it, and it points towards the center of motion, if there is any. And we have a temporary radius of curvature and a temporary center for that one instant. And this will move. If we look over here, we have a normal in this direction, but when it was up here further up the hill, the normal might be in that direction. So that's going to change as the roller coaster goes down the hill. So this forms the basis for our reference frame. And in this reference frame, recall then that we can say V is rho beta dot, and that would be in the t hat direction. And AT, the specific component of acceleration of t hat, would be v dot in the t hat direction, which is really just dv dt, and that is our A linear, which is a change in speed. Now we'd also have a normal, which could be written many ways. We could write it as rho beta dot squared, or v squared over rho, or v beta dot. So a lot of different ways to write it. We just pick whichever one is convenient for the case. And keep in mind that this is all centripetal acceleration. All right, so this forms the basis for our reference frame. If we take a look at this curve, they're giving us the general form cosine of kx, but we have to figure out what the real form is. So let's take a look at that for a second. We know the cosine function will generally look like this if we see the full wave. Where we would call this the amplitude A, and we have negative amplitude here, and this will be the wavelength, which is the point where our cosine pattern repeats again. And the general form is that y is equal to A, some cosine of kx in this case. A, if we take a look, is the amplitude, and k can be found as 2 pi over the wavelength. Now the wavelength in this case is, that's 100, it would be symmetrically another 100. So the wavelength is 200, so this is going to be 2 pi over 200, or pi over 100. And that would have units of 1 over feet. Now another problem that we have here is we're using the ground plane up here for our reference point, and we can do that. But in order to do that, y would be A plus A cosine of kx. We're basically adding A to all points of the curve, which is going to push it up higher in the air. All right. If we look at it that way, 2A is 40, so A is 20 feet. So with that, we can use this form, and we'll see that y is going to be A, 1 plus cosine of kx, where k is defined here, and A is going to be 20. So let's clear that away, and recall now that we have A equal to 20, and feet, and k is pi over 100 feet to the minus 1. And down here we can define y as A, 1 plus cosine of kx. Now to work in the tangent normal frame, let's find the derivative of y. The derivative of A would be 0 times 1. So we end up with negative A, k, sine of kx for the first derivative, and the second derivative is negative A, k squared, cosine of kx. If we plug everything in, we get 20, 1 plus cosine of pi over 100 times 75. Now keep in mind that that's in radians, so use care when you're putting that into your calculator. And we'll get a y value of 5.86 feet. And y prime be minus 20 pi over 100 sine of pi over 100 times 75, which will be negative 0.444. And this would be feet per feet, so it's unitless. And keep in mind that's not velocity, y prime. It's not a time derivative, it's a spatial derivative. So it's feet per feet. And lastly, we get minus 20 pi on 100 squared cosine of pi on 100 and 75, and we get 0.0140, and that'll be 1 over feet. There's a few things we can do with these values. One is, very nicely, that's the slope. And we'll be able to find the angle that this little roller coaster is making with respect to the horizontal. So from there we get theta is negative 24 degrees. Another very useful value that we need is the radius of curvature rho. We could find that mathematically using our formula from calculus. 1 plus y prime squared to the 3/2 power divided by y double prime. We get 1 plus negative 0.444 squared power gives the radius of curvature of 93.9 feet. Now from here directly we know that V is rho beta dot. So beta dot will be V over rho, which is 40 feet per second over 93.9 feet. And from there we'll get beta dot 0.426 radians per second. It's in that direction, which we'd call the positive b hat for the binormal. And recall that b hat is t hat crossed n hat. And that'll denote the positive b hat direction. We can draw a free body diagram. And on our free body diagram, we have our, we'll do a reference, the velocity v is here. That's theta, which we know is 24 degrees. Here's our mass m. And then perpendicular to that is the n hat direction. And this would be the t hat direction. So from there, let's build our free body diagram. So acting straight down, that's not straight. So acting straight down, we have the weight W. Acting perpendicular to the track is the normal force. And then acting up the hill, opposite direction of motion is the friction force, which we know would be mu k times Fn. And then working in our reference frame, to break W up into a normal and tangential values, if that's theta, then this is also theta here. So from there we get components of W cosine of theta in the negative n hat direction W sine of theta in the t hat direction. And with that we won't need the W. We have it in the components. And from here we can start. So sum of the forces in the n is MAN. And we could calculate AN. AN would be V squared on rho, which is 40 squared on 93.9 or 17.0 feet per second squared. So that acceleration we can calculate, and that's centripetal. We're on a slight curve over here. So this denotes the positive direction. So our equation becomes Fn minus W cosine of theta is MAN. And from here we can get Fn. So Fn will be W cos of theta plus MAN, which is 2,000 pounds times the cosine of 24 plus 2,000 over 32.2 times 17.0 feet per second squared. Here this denotes the mass as weight divided by gravity. So solving, we get a normal force of 2886 pounds. Which is just slightly larger than what the weight of the wagon is directly. If we take a look at the t hat direction, we can repeat the process. Sum of the forces in the t is MAT, and pick this as positive once again, right? So we have W sine theta minus mu Fn is equal to MAT, which is one of the things we're looking for. We know everything on this side. We can divide by the m, so we'll get 2,000 sine of 24 minus 0.2 for the friction, and 2886 is equal to 2,032.2 times AT. And with that, we'll get A sub t of 3.8 feet per second squared. So the wagon is still speeding up, even with friction involved. If you want to try one yourself, try x equal to 35 feet with v still 40, and you'll get a solution of AT of 12.